Good day, Gators. Today what I wanted to do was talk about stoichiometry. And I'm actually going to go through a PowerPoint that was presented by Mrs. Demink. So we have her to thank for this. So thank you, Mrs. Demink. Let me go ahead and start this. Maybe. There we go. So stoichiometry. And it's a really fancy word. And it basically is, talking about kind of cooking and ingredients in chemistry. So yeah, chemistry is just like cooking, but don't lick the spoon. Okay, now stoichiometry, technically it's the study of quantitative relationships that exist in chemical formulas and reactions. And it's probably best to kind of think about it in terms of, analogies. So let's say you had in your garage or something, you found two wheels, a body of a bike, a handlebar, and a gear chain, okay? And you could put those together to make a bike, right? Well, what would happen if instead you looked in your garage and you had 8 wheels and 5 bodies of the bike and 6 handlebars and 5 gear chains? And you want to know, well, how many bikes can you make? And then you have to kind of look at things where here, it's one body, one handlebar, and one gear chain are all needed for a bike. But notice you need actually 2 wheels, which means that with 8 wheels, we can only make 4 bikes. So even though we have more than that of these other ingredients, if you will, after 4 bikes, we run out of wheels. So you can only make 4 bikes, and then you have some leftover parts. And we can look at that visually here, where here's your initial parts. You can end up putting them together and getting your 4 bikes, and then there's a few remaining parts as well. Now, when we're thinking in terms of chemistry, really the key to this is balanced reactions and looking at the moles, both in the reactants and the products. So when you have a balanced chemical equation, the coefficients of that equation represent the moles. So what this is saying is 2 moles of NaCl reacts to yield 2 moles of sodium plus a single mole of chlorine gas. So if you're asked how many moles of salt are there, well, it's 2. If you're asked, how many moles of sodium are there? Once it's decomposed, again, you have 2. But in terms of chlorine gas, notice that the 2 chlorines bonded together to create a single particle of chlorine gas. Therefore, as a result of this, chemical reaction, we only have 1 mole of chlorine gas at the end of the reaction. So 2 moles of salt react to form 2 moles of sodium plus 1 mole of chlorine gas. Now, we can actually use that kind of thinking to do this process called stoichiometry. And there is a format where it's probably most easy to solve stoichiometry problems. The first key thing is you do need a balanced chemical reaction. Now, once you have a balanced reaction, do determine what do you have, what do you want. Okay, and then this you will be using for what's called a molar ratio, which will end up being 1/2, and we'll get into that in a little bit here. And then it's time for math, yay! Okay, so you'll frequently in DA have to do, and in stoichiometry, since we measure things in terms of grams, you'll have to often start with a gram amount and do a mass to mole conversion. And then since the chemical reaction is moles, you then do a mole ratio or a mole conversion, where you're going to be converting from your have to your want with this mole ratio, which is actually 1/2, since the halves will cancel out and leave you with the want. And then once you have the number of moles of whatever you're looking for, you often will need to convert that back to grams. So you'll have a mole to mass conversion. So frequently there'll be 3 DA steps in stoichiometry problems, going from mass to moles of your have, moles of your have to moles of your want, and then moles of your want to mass of your want. You might not always need all 3 steps, so pay attention to units. You might be given moles. You might only have to solve to moles. So it doesn't have to be all 3, but frequently it is. Okay, now in a molar ratio, what you're basically doing is comparing the 2 compounds in your calculation, and you're looking at, how many moles of what you're looking for or want do you have over how many moles of what you have do you have. So moles of want over moles of have is the molar ratio. Now, like we said, most of these conversions are gram to gram conversions. So here would be a problem. So we said, aluminum is an active metal that can be placed in hydrochloric acid, which we haven't really gone into acid naming in the general chemistry, but it's HCl in this case, and it produces hydrogen gas and aluminum chloride. How many grams of aluminum chloride can be produced when 3.45 grams of aluminum are reacted with an excess of the hydrochloric acid? So first thing you do, and we have this cute little owl here, is to write a balanced equation. So we have aluminum, which is a solid, plus hydrochloric acid, HCl, reacts to yield aluminum chloride. Now remember, you do have to do the balancing of charges. Aluminum is +3, the chloride ion is -1, so you need 3 chlorides there, plus your H2. Hydrogen is a Brinkelhoff element, so it's H2. Now, oops, I was going to do that. I was going to talk this through first, but we have aluminum here, then 1 hydrogen here, 2 there, which means you'd need a 2 here. But then you are set up with 2 chlorines and 3 chlorines. And when you ever see 2 and 3, think 6. So we're actually going to need 6 of these HCl's, which will then mean you'll have 3 H2s and 2 AlCl3s. Well, if we have 2 here, we then need 2 there. So we now have a balanced chemical reaction. And we can look at what we have and what we want. So we have the aluminum, 3.45 grams, and we want to know, well, how much aluminum chloride can I make? Well, let's do the math. Again, like in all the DA we've done, you start with your have and go to your want. So here's our want, grams of aluminum chloride. And you can do it, basically with a line with, breaking into blocks, or you can do it with, little line and then little multiplication signs. But here's our have. So we start with our have, 3.45 grams of aluminum, and go 2 grams of aluminum chloride. Well, the first step, like we said, is going from grams to moles of our have. And our have, again, is aluminum. So 1 mole of aluminum is 27.0 grams of aluminum, and that's from the periodic table. And we set it up with the ratio where the grams will then cancel, okay? And we're left with moles. Now this is moles of have, and we said the crucial next step, which is kind of new, this is a new thing, is to go from our have quantity to our want quantity. And you'll notice we have 2 moles of aluminum chloride get produced for every 2 moles of aluminum that are used. So in this case, our molar ratio is 2 moles of aluminum chloride over 2 moles of aluminum. Moles of aluminum will cancel, and we're left now with the moles of our want substance. So here we're not changing the units, we're changing the substance, going from here to there. And then finally, again, we generally will talk in terms of grams. So we convert our aluminum chloride back to grams. So 133.3 grams of aluminum chloride, and that's just adding up 1 aluminum and 3 chlorines, is 1 mole. we put the moles on the bottom so that moles cancel and we're left with grams. So then you would take 3.45 divided by 27.0 times 2 divided by 2, that kind of cancels out, and then times 133.3 grams of aluminum chloride will then end up with, well, yeah, and these will cancel, 17.0 grams of aluminum chloride. All right, and this is the general format, and if this kind of makes sense and you can do this, you can pretty much do any of the stoichiometry problems. Notice that when you do the DA, you should end up having the units matching. You know, here was what we were shooting for, and we started with grams of aluminum, and we did steps progressively canceling units until we got to our want units. So a second problem that you could do is, you know, same equation, but how many grams of aluminum do you need to produce 5.00 grams of aluminum chloride? So in this case, we're given this quantity and we need to know how much ingredient do we need? Well, same process. That's, you know, this is now our have, this is our want. So here we start with our have, 5.00 grams of aluminum chloride, and we kind of work backwards this time. So 1 mole of aluminum chloride is 133.3 grams of aluminum chloride. Grams cancels and we're left with moles. And then we have the mole ratio step, 2 moles of aluminum over 2 moles of aluminum chloride. And then finally, we have going from moles of aluminum to grams of aluminum after we've canceled the moles of aluminum chloride. So 27.0 grams of aluminum is 1 mole of aluminum. Moles of aluminum cancel, and we're left with grams. And when you do the math, 5.0 divided by 133.3, this cancels, times 27.0 equals 1.01 grams of aluminum. Once again, units match. Okay, now in the lab that we're doing this week, we will be looking at theoretical yield and percentage yield. Well, theoretical yield is when you do the math, when you do the stoichiometry, what number pops up, and that's the theoretical yield. Okay, ideally that should be the amount that you get in the lab. Frequently you'll get a slightly different value, either more if they're impurities or less if you lose some or something like that. But the theoretical yield is the yield from the math. Okay, what you really get is often called the actual yield, because that's what you actually get when you run the experiment. Now, percentage yield is then the actual, that's what you get doing it experimentally, divided by the theoretical, which is, again, what you get from the math, and then times 100. So this is similar to a percent error situation, but kind of different or opposite, because here we're shooting for 100%. We want to have the actual yield exactly equal to theoretical yield, in which case we get 100% yield. Okay, there is one other thing, and we'll go into this more detail in future weeks, but you can also kind of look into which reactant actually limits a chemical reaction. And once, just like that bicycle example, once you run out of the least parts, then the reaction will stop. Just like you couldn't make a 5th bike because you ran out of wheels. Okay, so what you run out of is called the limiting reactant. The other reactant or reactants that you still have leftover stuff is known as excess reactant. So here's an analogy. And you could figure out, how much product do you need? So if you have some bodies of cars and tires of cars, and you can make 8 cars. But you'll notice if you, do the counting out, you're going to end up with 16 extra tires that just, don't have a car to go with them. So just like before, to do the stoichiometry, balance the equation, do the DA, figure out your wants and your haves. And what I would recommend is just doing both reactants, from your have to your want, or, it could be products, but go from whatever your haves are, go to the wants both times, or, pick a want and go to that both times. And then whichever one produces the lesser amount is the one that ends up being the limiting reactant. Oops, this kind of goes in the way there. So for example, we have here a 2-gram sample of ammonia, is mixed with 4.00 grams of oxygen to produce nitrogen monoxide and water, which is the limiting reactant. Okay, so when we balance the equation, we get, this. 4 NH3 plus 5 O2 reacts to yield 4 NO plus 6 H2O. And it's not in this, you're just asking for a limiting reactant here, so it's not actually crucial to determine which one you go to. You just need to pick one in this case and go to it. Sometimes they might ask, how much NO do you produce? But here it's just asking which is the limiting reactant. So in this case, the person solving the problem went to NO. And it's the same methodology we just talked about, where you start with your 2 grams of your half, which was NH3. Then 1 mole of NH3 is 17.0 grams of NH3 from the periodic table. Then when we're looking at our mole ratio, we have 4 moles of our want for every 4 moles of the half. So our molar ratio here is 4 moles of NO over 4 moles of NH3. That will convert us to NO. And then using the periodic table, 30.0 grams of NO are produced in every 1 mole. So moles will cancel and we get 30. So then 2.00 divided by 17 times and divided by 4, that cancels, times 30.0 equals 3.53 grams of NO. So that's how much you could make with your NH3. But we also have another ingredient, is oxygen. And here, if we start with our 4 grams of oxygen, then 1 mole of oxygen, and this is oxygen gas, not just the element oxygen, so it has a mass of 32 grams of O2. And then here, notice the mole ratio is, again, our want 4 over our have 5. So 4 moles of NO divided by 5 moles of O2. And then, once you get to NO, use the molecular mass of NO per mole to then get to grams of your want quantity. And again, everything cancels in terms of units except grams of NO. And so it's going to be 4.00 divided by 32.0 times 4 divided by 5 times 30.0 equals 3.00 grams. Then we look here, this one makes less, which means that once we've got 3 grams, we're out of oxygen and we can't make the remaining 0.53 grams. So oxygen is the limiting reactant. Okay. Now, once we know that, you can actually calculate excess. And essentially, there's several ways to do it. One would be to start with your 4 grams of oxygen, convert to moles, and then use the mole ratio to NH3, which is your other reactant. So 4 moles of NH3 over 5 moles of oxygen, and then multiply by the mass there per mole. Everything cancels to get grams of NH3. And that's how many grams are needed to react with 4 grams of oxygen gas. So then, since we started with 2 grams, we needed 1.7 grams. Then there's a residual 0.3 grams of NH3 remaining. And there's a few ways to do this part here, but that's one of the methods. Okay, so that just hopefully gives a little bit of an overview of stoichiometry. And now if I can figure out how to stop. Oh, here we go.